Chem 201 Lecture 9 deals with bomb calorimetry. Bomb calorimetry is when we measure the heat of a reaction in a closed, insulated container. Typically, when this is done, gases build up so the pressure increases in the container, and we call it a bomb. Here's a schematic of the container. You notice it has water, closed walls, and a thermometer where the reaction occurs. This means our heat is measured at constant volume. Because the volume is constant, the gas we create cannot expand and do work, so no work is done, which means heat at constant volume is equal to the change in energy. So if we look at our formula, change in energy is equal to change in enthalpy plus minus nRT. I remind you that the enthalpy of a reaction, delta H, is the heat absorbed by the reaction at constant pressure. So if we look at this bomb calorimeter, it's insulated. So any heat the reaction creates plus the heat absorbed by the calorimeter must be equal to 0, or the heat the reaction generates is equal to the negative heat the calorimeter absorbs. In order to quantify this in terms of the calorimeter, we can say that the heat of the calorimeter is equal to capital C calorimeter times the change in temperature of the calorimeter. Capital C calorimeter is known as the heat capacity of the calorimeter, and delta T is equal to the temperature change in the calorimeter. Many times the water is the most important part of the calorimeter, but some calorimeters will have the walls absorb heat as well. So sometimes when you're working with a bomb calorimeter, you run a standardized reaction so you can calculate the heat capacity of that specific calorimeter. On the other hand, if you're working with a calorimeter where the walls do not absorb very much of the heat at all, and water is the only important part of the calorimeter, then we can simplify that the heat of the reaction is equal to negative mass of the water in the calorimeter times the specific heat of water times the change in temperature of the water. So here is an example problem using a calorimeter. We're going to burn 117.2 milligrams of naphthalene, formula C10H14, in a calorimeter, which results in a temperature rise of 3.275 degrees Celsius in a bomb calorimeter with a heat capacity of 1.378 kilojoules per degree Celsius. We're going to take this information and move it all the way to the heat of formation of naphthalene. In order to do this, first we need to write the balanced equation for the combustion of naphthalene at 25 degrees Celsius. So combustion, of course, is a material reacting with oxygen to make CO2 in the gas phase and H2O in the liquid phase, because remember, when we calculate the enthalpy of formation, typically these are done at 25 degrees Celsius, and most bomb calorimeters are designed so that their temperature stays close to 25 degrees Celsius. And of course, at 25 degrees Celsius, the state of water is a liquid. Our next question asks, what is the energy change of combustion of the naphthalene in kilojoules per mole? Here we can let the units of the heat capacity, which are in kilojoules per degree Celsius, and think about multiplying it by the temperature change, which is in degrees Celsius. So let's start there. The change in energy for the reaction is going to be equal to the negative heat capacity of the calorimeter times the temperature change of the calorimeter. So when we multiply those out, you notice we get minus 4.513 kilojoules. Now, first off, remember the sign change. It is a negative heat capacity of the calorimeter times the change in temperature. And we would expect this to be exothermic. After all, we are burning something. The other issue about this number of kilojoules is that it is only for 117.2 milligrams of naphthalene. We have been asked to get the answer in kilojoules per mole. So we need to proportion this for the amount we have. So you notice that if I take my milligrams of naphthalene and divide it by the molecular weight, I will wind up with 0.8733 millimoles. So this minus 4.513 kilojoules occurs for that number of millimoles. In order to get my answer in kilojoules per mole, I simply need to divide those two numbers. So I will take my kilojoules from my change in energy of reaction and divide it by my moles of material. And now I have a reasonable value for combustion, minus 5,168 kilojoules per mole. So now we have converted from the not 1 mole amount to the 1 mole amount value. Now let's move to part C. We want to know not the energy of combustion, but the enthalpy of combustion of this material. So now we need to think about what kind of work would have occurred if we ran the reaction at constant pressure. So I remind you that the change in energy of combustion is equal to the change in enthalpy of combustion minus delta NGRT. This is essentially saying heat at constant pressure plus work is going to give us the energy change of combustion. If I rearrange this, you notice that if we want to solve for the enthalpy of combustion, we have to take the energy of combustion, and I've moved this over to the other side. So it is now plus delta NGRT. So we have taken the heat at constant volume, and we are now subtracting the work to get the heat at constant pressure. So if I look at this reaction, you notice that I have 10 moles of product gas and 27.5 moles of reactant gas, so my delta NG is minus 3.5. So that means I can take my answer from part B, which is the energy of combustion, and add delta NGRT. So I will add a minus 3.5. R is, of course, this value, and we are solving this for 298K. Now, of course, be very careful with your units because my energy change is in kilojoules, my work will be in joules. So I need to make sure I convert that to kilojoules when I do my addition, and I wind up with an enthalpy of combustion of minus 5,177 kilojoules per mole. Now let's get to the last part of this. I would like to know the enthalpy of formation of naphthalene. And I can use this combustion reaction right here because the enthalpy of formation of CO2 is very well known and a standardized value. And the enthalpy of formation of H2O as a liquid also very well known. So I can set my enthalpy of combustion equal to my heats of formation of products minus reactants. And you notice I know every value but one. I have gotten this value from my corrected calorimeter, and these values are well known. This is what I'm trying to solve for. And of course, by definition, the enthalpy of formation of any element is 0. So now, rearranging the math, I can get the heat of formation of naphthalene as minus 758.9 kilojoules. So when you look at your enthalpy tables, this is what has happened. Thousands and thousands of chemists have run thousands of calorimetry experiments to figure out the heats of formation of many of the organic molecules that we use today. And yes, that was a very long example, but I hope it shows you how things connect together. So now it's time for our question. When 1.020 grams of ethanol was burned in a bomb calorimeter containing 2,400 grams of water, the temperature of the water rose. The specific heat of water were given as 4.18 joules per gram degree Celsius, and we would like to know the heat capacity of the calorimeter in kilojoules per degree Celsius. So I remind you that heat is equal to ms delta T, or the heat capacity of the calorimeter times the change in temperature. So the assumption we're making here is that our bomb calorimeter does not absorb very much in the walls, and the water is the most important part. So I may use these values to figure out what is the heat capacity of the calorimeter, because ms is equal to C. So I will take the mass of the water times the heat capacity of the water. And you notice initially I get 10,032 joules per degree Celsius. I am, of course, being asked for kilojoules per degree Celsius, so I will divide by 1,000, and I'm reasonably sure you can complete the calculation from there. Our next question in the same scenario asks us, what is the energy change of combustion in kilojoules per mole? So as we are in a bomb calorimeter, the change in energy of combustion is going to be equal to minus the heat capacity of the calorimeter times the change in the temperature. So I'll take my value from part A and multiply it by the change in temperature. And of course, as far as sig fig goes, my first value is good to 3 sig figs. And when I subtract the temperature, this will also be good to 3 sig figs. Now, when I get this value in kilojoules, it will be for 1.020 grams, which, if I divide it by 46.07 grams per mole, is 0.02214 moles of ethanol. So in order to get my energy change of combustion in values of kilojoules per mole, I'm going to have to take my answer for what I did the combustion on and divide it by the moles that actually underwent combustion. And that will give me my value. Now let's take this one step further and get the enthalpy of combustion. We know the energy of combustion is equal to the enthalpy of combustion plus work. So if we need the enthalpy of combustion, we need to take the energy of combustion and subtract the work. Work is, of course, equal to minus delta NG RT, so we need to write the balanced reaction in order to figure out our change in moles of gas. Here is our boilerplate reaction where ethanol reacts with oxygen to make gaseous CO2 and liquid water. That means I need a 2 in front of the CO2, a 3 in front of the H2O. I have 7 moles of oxygen on the product side, so that means I need 7 on the reactant side. 6 of them come from the O2, 1 comes from the ethanol. So that means delta NG is going to be equal to 2 minus 3, or minus 1 moles of gas. So our work is going to be equal to a minus 1, 8.314 joule per Kelvin mole times 298 Kelvin. This is going to give us an answer in joules per mole of our reaction. And of course, I know you need to convert it to kilojoule per mole of our reaction. Now we can take delta H combustion equal to our value of delta E combustion from an earlier calculation minus the value that you get for work. And substituting in those two values will give you your answer. Now, I could take this a little bit further and get us to the heat of formation of ethanol, but I think you've had enough. So just to summarize where we are now in Chapter 3, chemists view chemicals in phase changes and reactions as having a potential energy in units of heat, which are called change in enthalpy. In the standard state at constant pressure, it doesn't matter how the delta H for a reaction is measured. All paths should lead to the same potential energy difference between products and reactants. Some paths are more direct than others. So if we want to get delta H for a reaction, we might use calorimetry at constant pressure. We might use heats of formation of products minus heats of formation of reactants. Or we might use bonds broke minus bonds formed, and we might have to correct that for phase differences. All three of these methods should lead to the same answer. So just to remind you of all the formulas we now know, the main formula for Chapter 3 is the energy change is equal to heat plus work. Heat at constant pressure, we can get a number of ways. We can either get it for phase changes as ms delta T when we are changing temperatures, or N delta H if we are changing phase. We can get delta H from reactions by heats of formation of products minus reactants, or bonds broke minus bonds formed. Or we can get our enthalpy change using bomb calorimeters, in which there is no net change in the moles of gas of the reaction. Work only has one simple formula. Work is equal to minus delta NGRT. And if we want the full energy of the reaction, we can either add heat plus work or use a bomb calorimeter and use the negative heat capacity of the calorimeter times the change in temperature. So I hope that helps you understand how these formulas all fit together.